Okay, so guys, today's lesson we're going to talk about some further techniques of integration. Okay, so let's just give you two questions to think about. So these two questions are from our past exam or sample paper. So do you know how to integrate them? Okay, so you can use all the rules you've learned, try to integrate them, and and okay, so you might spend 5 minutes. Okay, so and try to think about this. All right, so let's just pause the video right now for a moment. I can't give you 5 minutes. Sorry, guys. So how about just 2 minutes, and you can see if you can solve that question, find some way to find the answer. Is that okay? So 2 minutes. Okay, so that's done. Okay, I guess none of you could find a way to get the answer because we haven't really learned about the integration of this type. Remember, integrations are very picky. You need the, the derivative for integration must be uh, well tailored for you to do integration. Okay, so that's why we need to learn some further techniques. All right, so let's go back to the origin of integration. Why do we need to learn integration? Okay, so let's just go back to our first slides from the beginning of it. Okay, so what's the relationship between these two functions? Okay, so some of you might have seen it. That's in your handout. So the left-hand side is actually, if you is the antiderivative, the right-hand side derivative. That means if you differentiate the left-hand side function, it will give you the one on the right-hand side, right? So we can go from left to right and from right to left. Okay, first of all, from left to right, you try to differentiate them. Okay, you just apply some basic differentiation rules. You are going to get cos 2x from the differentiation. Okay, how about going back? So by differentiation, you get the derivative. So going back, you are going to do anti-differentiation. Okay, so which means you take an integration on that's cos 2x, and you will get the antiderivative. So antiderivative on the left hand side, derivative on the right hand side. So most of the time in this chapter, we emphasize the process from the derivative to antiderivative. That's why we learn integration, and that's the true reason we need to learn integration, right? But sometimes, if the derivative is really like very complicated, then it's very hard to do integration. Then we can try to use another approach. We try to use the antiderivative to find the derivative to justify whether a certain answer is correct. Okay, it sounds quite complicated, so let's just go for our first example. Okay, so let's see the first example. You can see that fx equals half log x squared plus 3. Okay, so in part A, I'm asking you to find the derivative of fx and ask you to show. Show means a proof. You need to prove that. And the derivative is x over x squared plus 3. Okay, I trust most of you can do that. Okay, so let me just go to my handouts and try to get it done. Okay, here's my handout. Okay, so let's just try to do example 1 over here. So the keyword here is show. Show just means prove. So I need to prove that the derivative of such a fx is x over x squared x over x squared plus 3. Okay, so let's just do the differentiation. Okay, when we do the differentiation, we can kick that half out of the differentiation sign, and you're going to do this. We all know that you can't do it straight because the content inside the logarithm is different to x, so you can't go straight on this. So what I'm going to do is to apply the chain rule. Okay, so to do the chain rule, you are going to create that x squared plus 3 right here, and you get the chain of d bracket x squared plus 3 over dx. Okay, for the first part of it, it will just be half times 1 over x squared plus 3. That's the basic rule for differentiation of logarithm function. How about the other one? So just 2x. I trust most of you can do it, right? So, and then you will get x over x squared plus 3. Okay, so if you need some time to think about this, you can just ask the teacher to pause the video to let you think about this. All right. Okay, so no problem. Then we proceed. So you need to think about part B. Part B, I ask you to use the result of A. What do we mean by the result of A? That just means the derivative. The result of A just means the derivative of fx is actually x over x squared plus 3. And ask you to do the integration of that derivative. Okay, so it sounds familiar. Why? Because we understand if I got the derivative, if I try to integrate derivative, what are you going to get? You're going back to the antiderivative. Okay, so that sounds a little bit complicated in terms of those names. Let's say in that case, which one is the derivative? So this one is our derivative. So how about the function from which you get the derivative? That means this one. Yeah, so this fx is what we call the antiderivative. Okay, so part B just means you need to integrate what's the derivative. So you need to do the integration of derivative. So what will you get? You will get antiderivative in return, right? So let me say again, it's very important. So from part A, you get the derivative, and part B, they just ask you to integrate the derivative. Then what will you get? Antiderivative. So integration of derivative equals antiderivative. Okay, so that's how it is. It sounds like it's just like forming a circle. Okay, so you just go back to your original function. That actually is the case. If you think like that way, that's no problem with me. Okay, so part B. So if I write this one, that just means I'm integrating the derivative of fx. So let me use this notation to emphasize right now. What I'm doing is I'm integrating the derivative of fx. So from the definition of integration, when you integrate the derivative of fx, you go back to get fx plus c. And fx is just half log x squared plus 3 plus c. Okay, you just go back to the original function. Okay, but you still need to write that plus c because we understand that's indefinite integration. You always get that c. Okay, so that would be the structure for most of the questions in this part of further derivative, further technique for integration. Sorry, you always get to find derivative in part A, then they will just ask you how about the integration of that derivative. Okay, the trick is without part A, actually you can't do the integration in part B. So you have to apply part A to do part B. All right, so let's have a look. Okay, so this time, let me just jump to part B. So if I just miss out that user result part A, I ignore that user result part A. I just think about, is that possible for me to determine that integration without any other help from part A? Okay, you can think about this, but the answer is no. Okay, you can try, but you won't get your answer. Okay, so you really need to get that help from your part A. So part A is a function of fx, which equals e to the power x cubed plus 3x plus 5. Okay, so you need to again show the derivative is such thing. So when you compare that, the structure of that derivative to the integrand, okay, that means the content of that integration, they are very similar, okay, apart from you miss out a 3 in that integrand, but otherwise they are just the same. Okay, obviously they are related, okay, but you really need to prove that A first. All right, so how can we get the part A proved? So it's an exponential function. I trust you all know the derivative of a basic exponential function. Let me just give you like 2 minutes. Okay, let me give you 2 minutes on that part A, if that's possible. 2 minutes. Okay, let me just pause the video and you just. Okay, let's say 2 minutes has been passed. Okay, so what I'm going to do is try to get the derivative of that function. Okay, and obviously you can't go straight again because that's x cubed plus 3x plus 5 in the exponent, sorry. And so that means you need to apply the chain rule. I hope you all know how to do it, the chain rule. And the first part just the same thing as an exponential function. The second part, you need to differentiate the power of it. So just like this. Oh, sorry, I feel I missed out something in my question. Sorry, can you? Oh, sorry. Okay, can you add something here? Sorry, there's a typo right here. I just found out. Sorry, it's not my intention. So it should be 3x squared. Can you do that 3x squared over here? So 3x squared over here. Sorry about that. Oh, that means there's something wrong with my question now. So you need to make this 2. Sorry. I think I make a mistake in my PowerPoint as well. Really sorry about that. So it should be 3x squared. So it becomes 6x. Yeah, so that's a question. Okay, so give you some time to change that. Okay, so let's continue. All right, so let me put that 3x squared plus 6x to the front. And at the same time, I try to do a little bit factorization. I put 3x out. Then you will have x plus 2 here times e to the power x cubed plus 3x. All right, so here should be x squared as well. Oh my goodness, there are lots of mistakes. Yeah, so that should be the case. I think that's all good now. Okay, so after you've got this one, okay, remember to change the question for part B as well, all right? And you try to find the integration. Okay, let's write the integration right here. So you see that thing, the integrand here is very close to the derivative, but they are not entirely the same. Why? Because they miss out a 3 right here. So how can we do the integration this time? Okay, I'm going to try to express the thing I underline by green line to with the derivative of fx. Okay, so if the derivative of fx is 3x bracket, things like that. So all I need to do is try to get a 3 on it. Okay, so what I'm going to do is just I'm going to write 3 in front of it. Oh, yeah. I'm going to write a 3 in front of it. Oh, what happened? So let's. All right. But the problem is you can't just add a 3 because there's no such 3 in your original integration. So that means I better cancel that 3 out by writing a 1/3 out of it. So that's 1/3 times 3. So that means 1 actually. But when after I write that 3 in the integrand, you see that looks identical to the derivative, and that's what I'm going to do. So I'm going to do that as 1/3 integration. I'm going to rewrite that. Okay, again, so this is the integration of a derivative. So integration of a derivative becomes what? Integration of a derivative. Okay, let's try to say it together. It should be antiderivative, and the antiderivative just fx plus c, right? And your antiderivative in that case should be the fx, which is e to the power x cubed plus 3x squared plus 5. Okay, and plus c. Okay, so that's how it is. Oh, I need to write a square right here. Okay, I hope you can see that. Okay, that's how it works. Okay, so let's try to do a trigonometry one. Alright, so do we know how to integrate like a function 1 over sin x, sin square x? So of course we don't. We know how to integrate sine x, but not 1 over sine square x. It's another thing, totally different. Alright, so that's why we need to do part A. So when you see a question, they have word like hence, that means the results of part B depends on you're working in part A. So you need to apply the result from A to B. So again, in part A, you need to show a derivative. Okay, show a derivative. Okay, so let's try A. How can we get that derivative? So fx is like a cos over sin x. Cos x over sin x. So let me rewrite that into a, so we know for derivative, if it looks like a fraction, we could use quotient rule. Let me say that's cos x u and sin x is just v. Okay, so that means when I try to do derivative, I will get v squared, okay, v du over dx minus u dv dx. Okay, so that's the derivative of it. All right, and the v square, so our v right now is sine x. So sine square x. Okay, I will give you some time to fill in the rest of it because you really need some time to recall those differentiations. So let's give you another 3 minutes, possibly. Okay, to fill in all the things. If you can simplify them, then try to do so. Okay. Okay, so let's see what happens. So for v is sine x, so I put du, d is cos x over sine x right here, and u is cos x, and d sine x over dx. Okay, so let's get cos x. Du cos x means minus sine x, so it becomes sine x times minus sine x, so it becomes minus sine square x, and that d sine x is cos x, so cos x times cos x becomes cos square x over sine square x. Okay, so both are negative, so if I put that negative sign out, it make a bracket here, becomes minus bracket sine square x plus cos square x. So, but we know that when you have sine square x plus cos square x, that means 1, so it becomes minus 1 over sine square x. Okay, so that derivative actually equals minus sine x, minus sine square x. Okay, so let's try to get b done. So once you've got minus 1 over sine x, you see you need to find integration of 1 over sine x, sine square x. So you need to compare that's 1 over sine square x with minus 1 over sine square. Are they the same? No, but are they similar? Very, very similar. Okay, so the question is, how can you get that 1 over sine square x in terms of that derivative? If you can express that into derivative, then you know how to do integration. Just like, let me remind you our technique in our last example. So in our last example, actually when they give you that function, it's not entirely the same as the derivative. Okay, we miss out 3. Still remember how can I do it? So I simply put 1 over 3 in front of the integral sign and multiply 3 inside. Alright, so can you do the same? So I will give you just 1 minute to think about this. 1 minute to think about this. So I'm going to pause the video. Okay, so I hope some of you have got the answers. Okay, so first of all, of course, you need to copy that questions. Okay, the key is you need to get negative 1 there. Okay, so let's write negative 1 here to make it look exactly the same as the derivative. But by doing so, you have to do something outside the integral sign to cancel it out. How about I write another minus 1 times the whole thing? So because minus 1 times minus 1 just equals 1, all right? And within the integral, right now, it becomes f pi x. Okay, so against the integration of derivative, you will go back to derivative and antiderivative. So and the antiderivative is just cos over sine x, but you have a minus in front of it. That's it. Okay, just try to accommodate that minus inside the integral sign to make it derivative, but by doing so, I have to do something to counterbalance that effect outside the integral sign. That's the technique you need to learn. Oh, good. Yeah, so let's try another one. So this one looks quite interesting. So all you need to do is to prove. Okay, so that's another question in the past exam paper. You need to prove that that integral equals the right-hand side. So when you're asked to do the integration of the result of a certain integration, there are two ways to do it. So the first method, you might just do integration from left-hand side to right-hand side. You can try that if that's possible. And the second method, you do what? If you can't do integration, what can we do? You do differentiation. You do differentiation from right-hand side to left-hand side. Okay, so let's have a guess. Which is actually the intention of this question? Whether is are they really do they really want you to do the integration, or they just want you to show your understanding between the integration and differentiation? Okay, so in the exam, if you see that in the public examination, I will say 90% of the chance you should use second method. Okay, you can try first method. I could guarantee you from the skills you've learned, it's impossible for you to get it done, for you to do the integration to get the result on the right hand side. Okay, it looks simple. You have x times e to the power 2x. They look simple. Okay, both x and e to the power 2x, when they go separate, you know how to integrate them. But when they combine by making it as a product, it's impossible to solve. Remember, integration is very, very picky. Very, very picky. Even though each part of it feels very simple, that doesn't mean the combination of them is simple. They become very picky. Most of those those combinations are not integrable. So that means most of the cases you might just need to do the differentiation from the right hand side to left hand side. So let's try to do it. Let's try to see if that's the case. So let me just try to differentiate the right hand side function over x. Okay, let's try to do it. Half 2x minus 4 plus c. Okay, and it's not that simple, not that straightforward to do the integration of that one, but they are integrable. That's the main idea. All right, so you still need to do some hard work. Okay, let's just have this one. Okay, wait a moment. I got phone. Okay, sorry about that. Okay, so let's try to do this one. You can see for the first part, which really looks like a Porter rule, you can see that it looks like a u equals x, v equals e to the power 2x. So for the first part of it, you can use Porter rule for differentiation. And for the second part, just one chain rule away from solving it. Okay, so let's try the first part first. Okay, let's have a bracket because for the Porter rule, you need to have some room to write the whole thing. So that's Porter rule I'm going to use. Okay, for the second part of it, let me just use a chain rule. Okay. All right, so then I try to write the Porter rule. So I put x to the front and plus that one. Okay, so then you will get half. Okay, so let me do the second part first because that just look easier. So d2x over dx is 2, and multiply by 1/4 is 1/2, and that part is just e to the power 2x. So we understand that x times e to 2x, e to the power 2x over dx should be 2x e to the power 2x, right? You need to apply chain rule here as well, but I try to make it simpler. E to the power 2x, all right? Okay, so let's write the whole thing, all right? So I multiply that half into the bracket. So I'm going to have x e to the power 2x plus half e to the power 2x minus half e to the power 2x. Okay, so the last two terms, they just cancel out. All right, so let's see. So it basically means when you differentiate right hand side, you equals x times e to the power 2x. Okay, so that means if you differentiate the right hand side, you go to the contents of that integration. So that means what? That means x e to the power 2x is just the derivative of the it's just a derivative of right hand side. So that means right hand side is the antiderivative of x times e to the power x. So that means right hand side is just equals the antiderivative of x e to the power 2x. Okay, so in other words, you can just write the integration of that derivative equals the right hand side. Okay, so the proof is done. All right, so that's how we do the example 4. Right, so for example 5, it's a trigonometry functions. All right, so again, you have left hand side, you have right hand side. All right, so let me remind you, you can always think about whether we should go from left to right or right to left. But given the options, 90% or 99% of the chance, you should be using the second approach. You go from the right, you differentiate the right hand side, try to get into, try to prove that the derivative is just the things in that integral sign. All right, so we're going to do that. So again, for example 5, we will try to do the differentiation of right hand side rather than doing the integration of left hand side. Because okay, so even though again when you look at the left hand side, 3x is simple, right? Sine 3x is also quite simple in terms of integration, but when they combine, just impossible to integrate. So it's incredible. So every time you combine some simple stuff together for integration, you just can't work it out. It becomes much more difficult. All right, but that's not the same thing for differentiation. So differentiation is much less picky than the integration. So if that's possible, we always try to go differentiation rather than integration. Okay, so the idea is still the same. All right, so to start with, what are you going to write? Okay, so I'm going to give you 1 minute here to digest what we did in question 4, and you just emulate that kind of procedure for example 5. I just give you 1 minute to set up your initial step, your first step. Okay. Okay, so let's try to show you how can we get that right hand side differentiated. All right, so let me do it. The derivative of right hand side. So there are three parts of it. Let me just do it a little bit quicker. Okay, obviously we can separate this into three parts. And DC just equals 0, so I just missed that out. It's obvious. Okay, so again, if you look closely, and for the first one, it's just a Porter rule, right? Your U equals X, your V equals cos 3X. So they multiply together, and for the second part, all you need to do is a chain rule. Okay, so let's do it on the left hand side first. I'm going to write minus. Remember, you need bracket. Give it some room to write the Porter rule. And for the second part, you just need that chain rule. You just need that chain rule. Okay. For the first part, let's go with the Porter rule. Okay, so it's plus. Okay, so I'll give you some time. After you got this, can you do the differentiation? Okay, let me give you 2 minutes. Try to finish this off. Okay, let's say if you have done the 2 minutes. So if you haven't finished, you need more time, please just let the teacher know so you can spend more time on it. All right, for the first, okay, let me do the second part first. Okay, so the second part just equals 1/3, 1/3, that's cos 3x, and that's just 3. So 1/3 times 3, they just cancel out. So it's just cos 3x. And for that one, remember when you differentiate cos 3x, you need to do similar things like what we did for sine 3x. You need a chain rule for that. Okay, so let me assume you know how to use it. So it becomes 3 minus 3 because I d cos. So it's minus 3 sine 3x plus, okay, that's just cos 3x. That's it. Okay, then you remember that's minus sign outside the bracket, so you have 3x sine 3x minus cos 3x, then you have plus cos 3x. So obviously the last two terms are going to be cancelled out. Then you have 3x sine 3x. Okay, so let's go back to have a look. Right now, the derivative right hand side is equals, let me highlight this, equals 3x times sine 3x. Is that just the same as the integrand? So that means what? That means that 3x sine 3x is just the derivative of the right hand side. So in other words, the right hand side is just the antiderivative of that 3x sine 3x, right? So you can say, therefore, right hand side actually equals wrong spelling, sorry for that, antiderivative of 3x sine 3x. Okay, so in other words, right hand side actually equals integration of 3x sine 3x dx. Right? So that actually finished the proof. Okay, from the last two questions, I hope you have observed that when they ask you to prove the result of integration, actually it's more sensible to do it from right hand side to left hand side by differentiation. Okay, so integration is much more difficult than differentiation. Although for differentiation, sometimes you still need to know how to use Porter rule. Okay, but at least it's workable. It's viable approach. right? And we have, oh, that should be example. Sorry, I don't mean so. It's a silly mistake. So it should be example 6 rather than 5. Right, so, and there's another question in example 6, and the answer is in OneNote in the PowerPoint. Okay, I will just show you the answer straightforward, right? So, and that's on OneNote. Can I ask you try to work it out by yourself? Okay, because then you need to find the derivative, then you try to go back to do that one. So that means actually they are quite related. The two things are related. You try to link up the two things. Okay. All right. So you need to form fx. You need to get the derivative and try to link up that derivative with the integration. That's on OneNote. Okay. And so can you spend some time to work on this? I don't know. Possibly you need at least 10 minutes. Try to do this one. 10 minutes, and you might need some time to look back for some of the techniques I give you. Okay, and so after 10 minutes, I'm going to show you the solution from the textbook. Okay. Okay, so I guess I'm going to show you the answers. Okay. So first of all, you need to do a derivative. When you do a derivative, then you need to use the Porter rule. And from that Porter rule, you have log kx plus 1. Okay, so if you try to do the antiderivative on both sides, so that means you need to do the derivative on the left-hand side and also on the right-hand side. So the derivative on the right-hand side is just like integration log kx. You don't need to know how to do it because you are going to find that's integration, right? And you just get everything to the other side, you get the solution. Okay, so they use two constants in the textbook. That doesn't matter. When you try to do the subtraction, they becomes 1. Okay, so part B is more difficult. Okay, so if you try to do part B, if you have enough time to do it, then that will be the solution. All right, so there's some tricks there. If you don't really understand some part of it, okay, don't hesitate to discuss with me when we meet next lesson. All right, and okay, so please just have enough time to copy all the solutions. All right, and okay, so see you next time.